This is the last of the videos regarding domains of functions, and in this video we're going to cover exponential and logarithmic functions. Now of the two, exponential functions are by far the easiest to deal with because once you're able to recognize an exponential, effectively it's a constant base and a variable exponent, and of course the base has some restrictions. We have to have a non-negative base, but once you can recognize an exponential, as you see here, it's very easy to get the domain, because if you're just looking at a context-free exponential, then the domain is all real numbers. There's nothing you can put in there for the argument for x that is going to make those functions that you see on the screen ill-behaved. And so they're going to be well-defined for any real value of x, and therefore the domain of exponentials are typically all real numbers. Now, of course, if you impose some context and you have like an application, then that may change, depending on what you're working on. But anyway, in general, for context-free exponential, domains all real numbers. Now, when you invert an exponential function and you get a log function, then it's a little bit of a different story. And so the domain of log functions is a little bit more intricate. Now, before we dig in to the domains of log functions, it might be helpful to remember the notation that we use and the definition of a log function. So up at the top here we have the definition, and if I were to read that out loud to you, I would read it as follows. It's saying log base b of x is y if and only if b to the y is x. And that may not seem like it resonates well, or it may not be real helpful until you think about it a little bit. What it is saying effectively is that the log function tells you what power you're going to raise the base b to in order to make x. And b, the base, is strictly positive, meaning it's not zero, it's not negative, it's strictly positive. And so, since you can't take something positive and raise it to an exponent to make something negative, it should be clear why x, the argument, has to be strictly positive. Now, as far as the notation, it's also helpful to remember we use kind of a variety of different ways of writing log functions. So for example, if you're talking about log base e, of course being the natural base, we typically don't write it as log base e. We write it as ln of x. And the reason is because ln is an abbreviation for the Latin expression natural log. Likewise, for log base 10, the so-called common log, we don't typically write that with the base. We write it as simply log of x. And so it's helpful to remember when you're looking at these what the base is, because if you see ln of x, it's not obvious unless you know that the base is e. Likewise, if you just see log of x, it's not obvious unless you understand, hey, that's a common log, base is 10. So that said, if we were asking you about some of these log functions here and we wanted to know what's the domain, it should be fairly straightforward. The first one, for example, f of x. If I was reading that to you, I would read that as f of x is ln of x. We actually read the l and the n. And like we were saying, the domain of a log function, well, you have to have a strictly positive argument. So in the case of that first function, the domain would be x greater than 0. So in writing, in other words, we're saying, look, if you have a function ln of x, it's a log function. We know that the argument x has to be strictly positive, and so we must have x strictly greater than 0, meaning that the domain, however you choose to put it, would be the interval from 0 to infinity with a round parenthesis on 0, or if you're going to state it using set builder notation, x such that x is greater than 0. So that's a nice example, fairly straightforward. Let's look at what else we have. So what about the next function? G of x is log base 10 of the quantity 1 minus x squared. Let's talk about this one. For this function, we have to have the argument, which is the quantity 1 minus x squared, strictly greater than 0. And so as you've seen in a previous video, there's a couple of different ways of analyzing this. You can graph that particular function to get kind of a little bit of insight using your graphing calculator. And by that, I mean not the whole log function, but rather just the argument, 1 minus x squared. It's a parabola, and it has a y-intercept at 1, and it has roots on the x-axis at positive and negative 1. And so if you look at the graph, you should be able to see that it's positive. It's above the x-axis in between -1, and +1. And that's well and good, but we typically would want some kind of analysis on this. And so if I were to showcase that, here's what we've got. So here's the typical sign diagram that we would use for analyzing where some kind of a nonlinear inequality like 1 minus x squared is going to be strictly greater than 0. So we're looking for where it's positive, and you'll notice that I have open circles on the roots down there at the bottom, +1 and -1, because we don't want those. That's where the function 1 minus x squared is equal to 0. We want to avoid where it's equal to 0. We want to keep it strictly positive. So you can look at these two functions here that we've got as components, the 1 minus x and the 1 plus x. Both of them are linear functions. With regard to the first one, 1 minus x, it is a decreasing linear function. It has a slope of -1, and it crosses the y-axis at 1. It crosses the x-axis at 1 as well. You can look at the graph on your calculator if it helps. But anyway, that function is positive when you're to the left of 1, and it's negative when you're to the right of 1. So let's put that down. You can use the same kind of thinking with the test value if you want. So in other words, you could pick a value that's to the left of -1, and you could pick a value that's in between -1 and 1, and then you could pick a value that's to the right of +1. And you just put that in for x, and that's going to give you the sign. But I think that it's much easier and faster to look at this as a linear function. So anyway, with regard to the second component, 1 plus x, that is an increasing linear function, has a slope of +1, and it crosses the y-axis at 1. It also crosses the x-axis at -1. And so, as you can see, if you look at the graph, when you are to the left of -1, it's going to be negative, below the x-axis. And when you're to the right of -1, it's above the x-axis, which means it's positive. Now, as far as the product is concerned, you know that if you multiply two positives or two negatives, you get a positive product. And so as far as where we're positive here, it's going to be as follows. Positive times negative is negative. Positive times positive is positive. And negative times positive is negative. And so you can see here that we're positive, as we said, in between -1 and 1. And so that's the domain of this function. So however you choose to say it, using interval notation or set builder notation, that's the domain. From -1 to 1 with round parentheses on both ends, or if you prefer in set builder x such that -1 is less than x and x is less than 1. And of course, if you graph this on your calculator, you see the same thing. Now, certainly there's nothing wrong with using your calculator to confirm what we've seen. And as you can see here, here's the graph of 1 minus x squared. And it's positive in between -1 and +1. Now, as far as the graph of the log function, I think most people would probably go for that straight up. I don't know that that's more helpful. I think it's probably more helpful to see the quadratic argument first. But anyway. Yeah, sorry. So there's the log function right there. It's graphed in red, and you can understand why the domain is what it is. Let's take a look at the next example. For h of x is ln of the quantity x squared minus x plus ln of x. This is an intricate example. It's a very good example. There's a lot going on here, and so hopefully it will be of use to you. Let's take a look at what we've got. So as we've said before, if you have a function that has multiple pieces and you want the function to be well defined, all of the pieces have to be well defined. If one piece breaks down, then the whole thing breaks down. And so we have two separate pieces here. We have one which is ln of the quantity x squared minus x, and then we have a different one which is just ln of x. And so both of those pieces have to be well defined in order for the function to be well defined. So in other words, what we're saying is we have to have x squared minus x strictly positive, and we have to have x strictly positive. So there's an intersection that's kind of lurking in the background here. And so what we want to do is we want to find out where both of those are going to be strictly positive, and then we'll take the intersection, and that's going to give us our domain. So for the quantity x squared minus x, which is the one that requires the most analysis, hopefully you'd notice that that's factorable. It's x times the quantity x minus 1, and it has roots at x is 0 and x is 1. And so if you make the usual sign diagram, as you can see down at the bottom, you have those two quantities to analyze, x and x minus 1. Now as far as x is concerned, it's a linear function. It's increasing, has a slope of 1, and it crosses both the x and the y-axis at 0. And so in other words, you can look at the graph on your graphing calculator, but when you're to the left of 0, that's in negative territory, and when you're to the right, it's in positive territory. And likewise, the quantity x minus 1, increasing linear function, slope of 1, y-intercept of negative 1, crosses the x-axis at positive 1. And when you're to the left of that, it's negative, and when you're to the right of it, it's positive. Let's put this down. So you can verify that using test values, or you can use your calculator, whatever seems good to you. But again, we're looking at the product of those, and so if you multiply two negatives, you get a positive, and if you multiply two positives, you get a positive. And so let's put that down. So you can see that that quantity x squared minus x, it's going to be positive when you're to the left of 0 and when you're to the right of 1. But we have a second condition that we have to factor in here, namely x has to be positive. In other words, x greater than 0. So what we want to do is get both of these intervals down, and then we'll take the intersection, and that's going to give us our domain. So my diagram here is a little bit crude, but anyway, I have the set where x squared minus x is greater than 0 in green, and I have the set where x is greater than 0 in blue, and we want to intersect those two sets. So again, intersection meaning the overlap, the common ground. It should be clear that the intersection here is everything to the left of 1, or excuse me, to the right of 1, the other left. And the endpoint 1 is not included in the intersection because it's not included in the set in green. It would have to be an element of both sets in order to be included, and clearly it's not. So what's our domain here? Well, it's everything to the right of 1. And so whether you put it in interval notation or set builder, it should be fine either way. In interval, it would be the interval from 1 to infinity with a round parenthesis on 1. In set builder notation, x such that x is strictly greater than 1. Hope that's been helpful, and if you have any questions, please feel free to drop me a line.